So let's take stock of what we've done in solving this problem about someone base jumping off the top of a skyscraper. This particular example we won't be seeing again, but the methods we use to solve it we'll be seeing again many times in different contexts, so they're what really matter. So the first step was think about the physics. So we thought a bit about this. What are the forces acting? In this case, drag, gravity. We thought about the limiting cases. What are the limiting cases here? One limiting case when you've just jumped off the top, it's projectile motion, motion under constant acceleration. Later on, you're reaching a terminal velocity when the forces balance, which is a statics problem, though in fact most of the time is spent in between the two cases. We then did a very crude estimate, found out it would take about 2 seconds to reach terminal velocity. That wasn't actually very good, it's probably more like 5 or 6 seconds, but it gave us an order of magnitude of what we're talking about. It's not 0.0001 of a second or 4 hours or something like that. And then we approached it 3 different ways. We did it numerically, using both Excel and Python, and used calculus, and did a bit of graphical analysis. Which was the best way to deal with it here? Well, in this case, calculus worked pretty well. It was fairly easy and gave us a nice accurate answer. The numerical method also gave us a very accurate answer, but took a bit more programming to get it up and running. Does it matter that the calculus method is more accurate? Well, in this case, no. What are the things that would limit the accuracy? If you really needed to calculate this sort of thing, how long it would take to base jump off a skyscraper, let's say you were going to be a stunt director and wanted to time when someone would go past a window so you could film them in the background or something like that. The difference in accuracy between the calculus and the numerical approach is tiny, especially if you make a reasonably small step size in the numerical calculation. Much bigger uncertainties would be in the physics. What exactly is the cross-sectional area of a person? What is the drag coefficient? How will that change as they tumble over, as they fall? That's almost certainly a much bigger uncertainty, plus the fact that the drag equation, the drag force equals half CA rho V squared, is a very approximate equation, as you may remember. That's not very good at all. It's the fudge factor C often varies with speed. So that is almost certainly the really big approximation, and the difference between the numerical and the calculus ones is almost irrelevant in comparison. So now we'll go on and see how we apply these methods to a wide variety of other problems.